In the previous video, I discussed the scalar or the dot product. In this video, I will discuss the vector product, which is also called the cross product. After the discussion, we will be solving two example problems. So, if you're ready, let's begin. The cross product of two vectors is a vector whose magnitude equals the area of the parallelogram formed by the two vectors and whose direction is normal to the plane containing the two vectors, as defined by the right-hand rule. So this is how we define the cross product. Now, to illustrate this definition, let us have two vectors A and B. So here they are. This is vector A and this is vector B. Now, if we will project these two vectors on the opposite sides, we can form a parallelogram. So this is the parallelogram that is formed by projecting vector A. This is vector A and this is the projection of vector A. This is vector B and this is the projection of vector B. If we know the angle between the two vectors, so this is the angle theta, we can determine the area of the parallelogram using a known formula in geometry. So here, if this side has a length equal to A, which is the absolute value of vector A, and this side has a length B, which is equal to the absolute value of vector B, then a formula in geometry tells us that the area of this parallelogram is the product of the length of the sides, A and B, multiplied by the sine of the angle between them. So this is the area of this parallelogram. But since the cross product is a vector, we have to indicate its direction as well. The direction of the cross product is specified by a unit vector that is normal to the plane containing the two vectors. So these two vectors, A and B, they form a plane. The cross product is in a direction that is normal to that plane. So in this case, we have AN. This AN is a unit vector that indicates the direction of the cross product. So this AN is a unit normal vector. That's why the subscript is N, because it's a unit normal vector. So let us go back to our definition of the cross product. Remember that the cross product is a vector whose magnitude equals the area of the parallelogram. So now this is the area of the parallelogram. The only thing required is for us to indicate the direction of the cross product. Why? Because the cross product is a vector. It has to have a direction. And again, the direction of the cross product is indicated by a unit normal vector AN. No? And that a unit normal vector is always normal to the plane containing the two vectors. Okay, so now let's write down the cross product A cross B. No, that A cross B is equal to AB sine theta multiplied by a unit vector AN. So again, this cross product is a vector product. Sometimes it's also called the outer product in some references. Now, how does the vector A cross B look like? Okay, this is vector A cross B. And the direction of this cross product, of course, is this AN. Now, how do we get the cross product of two vectors given in three-dimensional Cartesian coordinates? For example, vector A is given as AX plus AY plus AZ. And likewise, we have another vector B, which is given as BX plus BY plus BZ multiplied by AZ. So here, this AX, AY, and AZ are the vector components, while this AX, lagyan natin ng arrow, AY and AZ are the unit vectors indicating the directions along X, along Y, and along Z axis. So what if we are given these two vectors? How do we get their cross product? To get the cross product, we just write these two vectors as a matrix like this. Okay, to get the cross product A cross B, we first write the unit vectors AX, AY, and AZ on the first row. On the second row, we write the component vectors of the first vector. In this case, that's vector A, and followed by the second vector, vector B. What are the components of vector B? These are Bx, By, and Bz. So now, to get the cross product, we need to evaluate this determinant, no? To evaluate this determinant, I will teach you a shortcut. Okay, for Ax, we cover the column containing Ax and multiply the remaining. So that will be down minus up. Okay, so that's AyBz minus AzBy. Now, for Ay, we cross out the column containing Ay, and this time, we multiply up minus down. So that will be AzBx minus AxBz. And lastly, for AZ, we cover this column and multiply down minus up, just like for AX. AxBy minus AY times BX. Okay, so if we write it down, we will get this. Okay, for AX, that's AYBZ, ito yun, minus AZBY. And then for AY, it should be this, so AZBX minus AXBZ. And for AZ, we cover the third column and get the product down minus up, AXBY minus AYBX. Okay, so there you go. You already know how to get the cross product of two vectors if they are given as three-dimensional vectors in Cartesian coordinates. Now, let's discuss the various properties of the cross product. First, the cross product is not commutative. Remember that in our discussion of the dot product, A dot B is the same as B dot A. So, the commutative property applies to the dot product, but that is not true for the cross product because the cross product is not commutative. As a matter of fact, it is anti-commutative. Why? Because if we commute the two, for example, we have A cross B and we commute it, we'll get a negative answer, no? So A cross B is equal to the negative of B cross A. So remember, the cross product is anti-commutative. Next, the cross product also is not associative, no? It's not associative. So A cross B cross C is not the same as A cross B and then cross C. Unlike in the dot product. If you recall, in our discussion of the dot product is associative. However, the cross product is not. Next, cross product is distributive. So if we have this expression A cross B plus C, that is the same as A cross B plus A cross C. So again, although the cross product is not commutative, it's not associative, the cross product is distributive. Now let us recall that the cross product of vectors A and B, so let's write it down, A cross B, let's put some arrow on top to indicate that they are vectors, is equal to the product of their absolute values, AB, multiplied by the sine of the angle theta between them. Now, if the two vectors are parallel, then the angle between them is 0. And thus, the cross product would be 0 because sine of 0 is 0. The same is true if the two vectors are antiparallel or opposite. If two vectors are antiparallel or opposite, the angle between them is 180 degrees and the sine of 180 is also 0. Therefore, the vector product of two parallel or antiparallel vectors is always 0. Okay? Remember this. Another way of saying this statement is that two vectors are parallel or antiparallel if and only if their vector product is 0. Now, this also applies to unit vectors. Why? Because the cross product of two identical vectors is always 0. Why? Because if we have two identical unit vectors, for example, AX, and I cross it to AX as well, these vectors are identical, meaning the angle between them is 0, and therefore this rule applies. That's why the vector product of any vector and itself is always 0. How about the cross product of different unit vectors? For example, AX, AY, and AZ. Now, if you are using a right-handed Cartesian coordinate system, the right-hand rule can be applied to determine the resulting cross product. So how do you use the right-hand rule? You just curl your four fingers from the first vector towards the second vector. And the direction of your thumb determines the cross product. Now, another way of determining the cross product of these unit vectors, AX, AY, and AZ, is with the use of a cyclic diagram like this. Here, we arrange the unit vectors sequentially in a clockwise manner. So we started here with AX, followed by AY, and by AZ. For example, we want to know the cross product of AX and AY. So the cross product of AX cross AY must be equal to AZ because it's the remaining one. But if we reverse the order and get the cross product AY cross AX, again, the remaining unit vector is AZ. But this time, the answer would be negative. Okay, it will be negative AZ. Okay, so here we can see that this rule applies. If we reverse the order of the two vectors in a cross product, our answer becomes the negative of the original. Okay, so if AX cross AY is equal to AZ, then if we interchange them and get AY cross AZ instead, we will get negative of AZ. So the rule here is that for clockwise multiplication, the answer is positive. And if we multiply the vectors here in a counterclockwise manner, the answer would be negative. So applying this rule, we will get the cross products AX cross AY is AZ, and AY cross AZ is AX, and AZ cross AX is AY. But for example, if we get AX cross AZ, because it's counterclockwise, the answer would be negative AY. So I think this is an easier way for us to determine the cross product of two different unit vectors in Cartesian coordinates. Now that you already know the definition of the cross product and its properties, it's time to solve some example problems. Here's the first example. Given the vectors A equal to 3AX plus 4AY plus AZ and B equals 2AY minus 5AZ. So this is three-dimensional while this one is two-dimensional. Find the cross product and use it to find the angle between the two vectors. Okay, so here we cannot use the definition that A cross B is equal to AB sine of theta. Why? Because here we don't know the angle between A and B. So what we can use is the determinant method. If you recall, A cross B can be obtained by evaluating the determinant. So first, we write down the unit vectors AX, AY, and AZ. Then the components for the first vector. In this case, it's vector A. So we write down these components on the second row. The components of vector A are 3, 4, and 1. 3, 4, and 1. And for the second vector, vector B, its components are, okay, for AX, it's 0. And then for AY, it's 2. And negative 5. Okay? Now, to evaluate this, A cross B, if you remember the shortcut, for AX, it should be 4 times negative 5, right? That's negative 20 minus this product, which is 2. and then multiply it by ax, and then plus. For ay, we will cover the second column, up minus down. So this product is 0 minus, so we have 3 times negative 5 is negative 15. So this becomes positive 15, and multiply it by ay. And then for az, we cover the third column, down minus up, 6 minus 0, and multiply it by az. Okay, so we can simplify this to get the cross product a cross b. So this is negative 22 ax plus 15 ay plus 6 az. So that's it. Ganun lang kadali. It's very easy. It's quite easy. Now, how about the angle between the two vectors? To get the angle, we need to determine the absolute values of A and B. Okay, so to get the absolute values of A and B, let's just use a calculator. For vector A, the absolute value is the square root of 3 squared is 9 plus 4 squared is 16 plus 1 squared is 1. So we have square root of 26. Let's write it down. Square root of 26. How about the absolute value of vector B? For vector B, its absolute value is the square root of 2 squared, which is 4, plus negative 5 squared, that's 25. So here we get square root of 29. Square root of 29. Now, using the definition of the cross product, A cross B is equal to AB sine theta, we can get this angle theta from this expression. However, we should get the absolute value of the cross product. The absolute value of A cross B equals, with the use of a calculator, that's the square root of 22 squared plus 15 squared plus 6 squared, that's 36, equals square root of 745. Okay, square root of 745. Now, we can use this to solve for theta. Theta is equal to the sine inverse of the absolute value of A cross B divided by A times B. So, this is the absolute value of A times the absolute value of B. Okay, so with the use of a calculator, we now have sine inverse. So, shift sine. Lagyan natin ng fraction sign. In the numerator, we have the absolute value of A cross B. That's the square root of 745. And in the denominator, we have square root of 26 times the square root of 29. So, that's the same as the square root of 26 times 29. We enclose them in a parenthesis and press the equal button. So, we now get 83.73 degrees. So, this is equal to 83.73 degrees. That's it. We're able to solve this problem, no? This is the cross product and this is the angle between these two vectors. So if you notice, it's quite easier to get the angle between the two vectors using a dot product rather than a cross product. Sir, can we use the vector mode of a calculator to get the cross product? Yes, of course, we can. To do that, we just have to put our calculators in vector mode. So that's mode vector, which is 8. So we create vector A by pressing 1. It's a 3-dimensional vector. So, we press 1 and input the vector components 3, 4, 1. 3 equals 4 equals 1 equals. And then, shift vector and then data. Now, we'll create vector B by pressing 2. Also, vector B is a 3-dimensional vector. So, we press 1. So, what are its vector components? 0 to negative 5. So, 0, 2, and negative 5. Okay, so the vectors are now stored in the calculator. So, if we want to get the cross product, you just recall the two vectors. Shift vector, vector A. For the cross product, use the multiplication sign, no? Cross. And then shift vector, vector B. So, 4. and then press the equal sign. So now we get the answer, negative 22, 15, and 6. Just like our answer here. Okay? So now we're able to show that the two answers are the same. So we're confident with our answers. Parehas sila eh. Now, how about the angle? Can we use a calculator in vector mode to get this angle? Yes, we can. So we just write the expression shift sign inverse of what? The absolute value of the cross product. So the cross product is actually stored as vector ans in the calculator. However, we have to get its absolute value. So we press shift abs or shift hip for the absolute value of what? Of the vector answer. Okay, shift vector, vector ans. The last vector answer is actually stored in vector ans. Okay? So 6. And divide it by, so we use the fraction sign, no? Divide it by the absolute value of A times the absolute value of B. Okay, so to get the absolute value, shift hip for the absolute value of what? Vector A. So shift vector, vector A, and close parenthesis. And then times the absolute value again, shift, and then hip for the absolute value of vector B. Shift vector, vector B4. And then another close parenthesis. So we press the equal sign, we will get 83.73. Just the same as our previous answer using the conventional calculation. So now, you already know how to get the cross product using the conventional solution, and also you can use the vector mode of a calculator to calculate the cross product, even the angle between the two vectors. Okay? So let us solve another example. Find a unit vector that is orthogonal to both vectors A and B. Okay, so how do we get a unit vector that is orthogonal to both A and B? If you recall, the cross product A cross B, so the cross product is a vector product whose direction is always normal to the plane containing A and B, right? So if the answer that we will get here has a direction that is normal to both A and B, then that is the vector that we're looking for. Okay? We should get the cross product A cross B, because their cross product is normal to both of them. However, we should find a unit vector. So after getting the cross product, we just divide it by its absolute value to get the unit vector. Okay, so that's what we're going to do. Okay, so we will use the conventional solution A cross B using the determinant. Okay, AX, and then AY, and then AZ. Now, let's write on the second row, the vector components of A. It's 1, negative 4, 1. 1, negative 4, 1. And for vector B, it's 2, 3, and 0. Okay, so how do we evaluate this? A cross B equals, for AX, that's 0 minus 3. So that's negative 3. AX plus, for AY, it's 2 minus 0. So that's 2 AY. And for AZ, okay, that's 1 minus negative 8. That's 3 minus negative 8. That's 3 plus 8. So that's 11. So 11 AZ. So this is the cross product. Now, what is the unit vector that we're looking for? Okay, to get the unit vector, we just divide this vector. For example, let us call this vector C, for example. So the unit vector in the direction of C is equal to negative 3AX plus 2AY plus 11AZ divided by the absolute value. So what is the absolute value of this vector? Using a calculator, let's go back to mode 1. Okay? The square root of negative 3 squared is 9 plus 4 plus 11 squared is 121. Okay? So this is square root of 134. Okay? Square root of 134. Okay? So if we get the quotient of each term, Gawin na lang natin yan sa fraction, no? So, negative 3 over the square root of 134. Okay, so this is equal to negative 0.259. Negative 0.259 AX. How about for AY? So I'll just replace negative 3 by 2. The answer is positive 0.173. Rounded to 3 decimal places. 0.173 AY. And for AZ, I replace this with 11. I will get the 0.95. No? 0.95 AZ. 0.95 AZ. So to check, if we get the absolute value of this vector, it should be unity, or it should be 1. If not exactly 1 because of some rounding off, then it should be very close to 1. Okay? Square root of negative 0.259 squared plus 0.173 squared plus 0.95 squared. Okay, so we're able to get this answer, 0.9997, which is obviously very close to unity. So again, we're not able to get an exact answer of 1 because here we rounded our answers to 3 decimal places, and the last term is rounded to 2 decimal places. So that's it. We're able to solve 2 examples already. So I hope that with these examples, you can now solve problems involving cross products. So if you like this video, don't forget to hit the like button and share this to your friends who are also studying engineering, because sharing is caring. Thank you for watching. Bye!